Good afternoon. My phone is low on battery, so I won't be playing music today. Um, Today, we are going to be talking about the normal distribution. The normal distribution. What makes it special? Why is it so interesting? Well, if you were to collect data from all over the world for tons and tons of different things, and you were to plot the histograms, they would follow a normal distribution for tons and tons and tons of different kinds of experiments. Okay, so I'm just going to dive right into the notes and run through some examples. Here is a regular normal distribution. The point in the middle of the normal distribution is your mean. Okay, back to the normal distribution. So we have the mean in the middle, and there are some key points on the normal distribution that are these lines, these tick marks right here. And these points are all separated. They're one standard deviation in width, okay, to the right and to the left. So that the points along the x-axis are x bar plus sigma, x bar plus 2 sigma, and x bar plus 3 sigma. To the left, it's x bar minus sigma, x bar minus 2 sigma, and x bar minus 3 sigma. Okay? And what makes them special is that we know there's some math in the background, but after that math, we determined that 34% of the data is in this piece, 34% of the data is in this piece, okay? 13.5% is in here, 13.5 is in here, and the two tail pieces, this is 2.35, and this tail piece is 2.35%. Okay? A key point is that this does not end here. This continues on to positive infinity, and this continues on to the left to negative infinity. Okay? This curve never touches 0. It just constantly approaches it. It just floats above 0. So, as a practice problem, let's actually do page 3 in the notes. So if the SAT critical reading scores are approximately normal, so we know we can use the normal distribution, with a mean of 505 and a standard deviation of 110. Part A asks us to draw and label the normal curve for the situation. So I'm going to start with just my basic drawing. Okay. The point right in the middle is the mean, so it's going to be 505. I'm going to scoot to the right by 110, so this is going to be 615. If I keep doing that, the next block, 110, so that'll be 725. And then if I keep going by another 110, that'll be 835. To the left, we're going to have 395. And we get that by doing 505 minus 110. Okay. I'm going to subtract off again, and that gives me 285. And one last time, 175. In general, you never go more than, you don't care about anything outside of 3 standard deviations away. So once you hit that 3 standard deviation mark, you're done. Let's fill in the percentages. .35 and 2.35. Okay. So, part B, between which two scores do approximately 68% of scores fall? So, the middle 68% is located right here. This is where 68% of the values are. 34 plus 34 is 68%. So the answer to this is the 395 and 615. So between 395 and 615. Okay. What percent of scores are greater than 615? So here's my 615. We're looking for scores that are greater than 615. I don't stop here. I keep going to infinity. I'm going to keep going to infinity. Okay? But we don't know the area underneath this tail piece right here. Okay? However, there is some information we do know. This is the mean of the graph. It's also the median of the graph, aka the median. And what do you know about the median? It divides your data set into two. Half of your data is above the median, half of your data is below the median. So from the median all the way to positive infinity, if I had a curve, I'll shade it in green if that helps. So from the median all the way to positive infinity, that's 50%, the green area, all of that green area, okay? We're only interested in this purple area. Let me color it over in purple again. Only interested in the purple. So how can I get the purple area? I'm going to take the total of 50%. And I'm going to subtract off this green area that I don't care about. So 50% minus 34%, that gives you 16%. 16%. So from here all the way to positive infinity is 16%. What percent of scores are between 505 and 615? Running out of colors. So let's see if we can see orange. 505 and 615, that's this piece right here, 505 to 615. So that has its own block, which is 34%. Between which two scores do approximately 95% of scores fall? Well, let's count. I know that 34 and 34 gives me 68. So let's see what these four give me. From 13.5 to 34 to 34 to 68. Off to the side. 34 and 34 is 68. Plus 13.5 plus 13.5. 17.5. Oh no, look at that. 95%. Okay. So from here to here is 95%. So it is between 285 and 725. 285 and 725. Alright. For this one, what percent of scores are less than 285? So I'm going to do that one with green. Less than 285. 285 is right here on my curve, and I'm going to the left all the way down to negative infinity. Okay, so I'm going to use the same trick as before. I know that here's my curve. From here all the way to the left is 50%. But I'm only interested in this piece to the left, this piece right here to the left. So I'm going to do 50% minus this piece right here, which is 13.5%, minus this piece right here, which is 34%. And that gives you 2.5%. That gives you 2.5%. Okay. And the last problem. What percent of scores are between 395 and 725? 395 is right here. 725 is right here. I'm just going to go over that with a black marker. All of those pieces right there. 395 to 725. So we're going to have 34% plus 34% plus 13.5%. And that gives you 81.5%. Okay? 81.5%. Another thing we need to be comfortable with is something called the z-score. The idea of the z-score is it's the number of standard deviations away from the mean. So if, say for instance, here is your normal curve, here's your mean. Let's say you move to the right by 1 standard deviation. This point right here has a z-score of 1. So this corresponds to z equals 1. It's 1 standard deviation away. 1 standard deviation to the right. This right here, where we're about halfway, this is z equals 0.5. 0.5 away. If we move to the right by 3 standard deviations, let's say we're at x bar plus 3 sigma, you're going to be at z equals 3. Okay. On the left-hand side, if you're at x bar minus 2 sigma, you're going to be at z equals minus 2. You're minus 2 standard deviations to the left. So it gives you a gauge of how far to the right or how far to the left you are from the mean. A key point here, the farther you away, the more standard deviations you are away, the higher your z-score, the closer you are to being in the tails. So this might be like a z of 10. This is very unusual data. Very unusual. Another word for that is statistically significant. Statistically significant data is located in the tails. Statistically significant data. The lower your z-score is, the closer you are to being more like the average. Okay, so the formula for the z-score is data value minus your mean divided by standard deviation. So in your calculator, x bar, another word for x bar is mu. And we're going to use that in a little bit. Okay. So, let's look at this practice problem. Recall that the distribution of heights of U.S. males 20 years or older has a mean of 69.4 and a standard deviation of 4.7. Okay. So what is the z-score for a man who is 72 inches tall? So your z is going to be your data value, which is 72, minus your mean, 69.4, divided by 4.7, which is your standard deviation. So if you do that, the z-score is 0.553. So this person, 0.553, is about right in here. Okay? They're less than 1 standard deviation away from the mean. They're pretty close to the mean. Current NBA player Dwight Howard is 83 inches tall. What is the z-score of his height? 83 inches tall. Well, I know Dwight Howard plays basketball, so I am expecting him not to be average, not to be anywhere in this bell. Okay, so let's see if that z-score confirms what I think. His z-score is going to be 83 minus the mean, 69.4, divided by 4.7, the standard deviation. So if I do that in my calculator, he has a z-score of 2.894. So Dwight Howard, I'll color him in orange, is about almost 3 standard deviations away. So he's farther away from the mean. Cool. Just like I thought. Part C. Former NBA player Spud Webb is 67 inches tall. So he's one of the shortest players in NBA history. The z-score of his height is, so z-score is 67 minus 69.4 divided by 4.7. And that will give you a minus 0.511. So he is located to the left. Maybe right here. So to the left means he's shorter than the mean. He's shorter than the mean. Tom Cruise is 67 inches tall and Jay-Z is 74 inches tall. Who has the more unusual height? So 67 inches, we actually just did that one right here. It's minus 0.511. Let's see Jay-Z. Jay's z-score is 74 minus 69.4 divided by 4.7. So his z-score is 0.979. So right here, this represents TC, or Tom Cruise. Jay-Z is 0.979. He's almost 1 full standard deviation away. There's Jay-Z right there in purple. Maybe kind of hard to see with all the lines. Here's the mean. And we're looking at Tom Cruise and we're looking at Jay-Z. This distance is bigger than this distance. So the distance from the mean to Jay-Z is 0.979. The distance from the mean to Tom Cruise is about 0.5. So Jay-Z is farther down the curve. He is more unusual. So that would be Jay-Z. The last part of the lesson talks about sometimes you're asked to find the percentage of something happening even though it's not one of your key points along the curve. So we did problems where we found things that were percentages that were like higher than this, or between this and this, or between this and this. But what if I asked you, what percentage of your data is between here and here? How much is being taken up by that? Okay, how would you do that? Well, based on what we've learned so far, we don't know how to do this. However, your calculators have a lovely feature in them that enables you to key in some key information, and then it gives you this proportion. Okay, so before I show you that, we're just going to go over some key terms. So information you need before you plug into your calculator. You're going to need LB, or the lower bound that you're finding the area of, and that's just the smallest value. You're going to need UB, or upper bound, and that's going to be the highest value in your interval. You're going to need X bar, which is your mean, and you're going to need sigma, which is your standard deviation. So once you have all that information, you can plug it in your calculator. It will save the day. So let's go through let's do part C as our first practice. Roughly, so now we're talking about WNBA players. It has a normal distribution with a mean of 74 and a standard deviation of 2. Okay, and right here are the instructions of how to do this in your calculator. Okay, and what goes into the function, and we'll see an example of this. You'll have the lower bound here, the upper bound here, your mean is going to go here, and your standard deviation will be there, and they're all separated by commas. So let's go ahead and get started. We have our mean, our standard deviation. In part C, we're looking for players that are between 67 and 75 inches tall. 67 and 75. So if I draw just a little reference diagram here, my mean is 72. I'm looking between 67 and 75. Okay? So it's not perfect, it doesn't have to be exact. So my lower bound is going to be 67. My upper bound is going to be 75. Lower bound 67, upper bound 75. So let me go ahead and go through the steps of how to generate this the first time. Just in your calculate screen, you're going to push menu and go down to statistics and go down to distributions, and then make sure you pick norm CDF, not norm PDF. Okay, our lower bound is 67. Our upper bound is 75. Our mean, so mu, that's another symbol for mean, so mu equals X bar. I wish they would use the same notation in every application. I apologize. Mu is X bar. So our mean is 72. And our standard deviation, stupid light, our standard deviation is 2. And then you just push OK. And look right there. It tells you 92.926983. So let me write that. 0.926983. I'm going to convert it to a percent, so it is 92.698%. And there you go. Just as a quick note, I'm going to do parts A and B as well. Approximately what percent of WNBA players are shorter than 69 inches? So I'm going to draw my reference. I think it's always helpful to draw a quick sketch of your reference curve. My mean is 72. I'm looking for 69 and lower. 69 and lower. So I need to find my lower bound and upper bound. Well, this graph right here, it doesn't stop anywhere. It keeps going, and it keeps going, and it keeps going. And the word for that is negative infinity. Negative infinity. And it goes from negative infinity all the way up to this point right here, which is 69. Unfortunately, your calculator does not know negative infinity, but it does know really, really small numbers. Numbers that are really, really far, really, really big and really negative. And we're going to call really big numbers negative 9e999. We're going to let that be the biggest negative number that's as close to infinity as possible in your calculator. This is the same thing as saying negative 9 times 10 to the 999 power. So let's go ahead and plug into our calculator. Rather than going through the steps again, I'm just going to go up here. I pushed the up button 2 times and pushed enter, and I'm just going to go in and edit the entries that I care about changing. So the first entry needs to be the lower bound. The first entry needs to be the lower bound. So negative infinity, let me put my negative symbol in. Let me zoom out a sec. Negative 9, and then E is this E right here next to A. It has 2 E's on it, so negative 9E999, comma, upper bound for this problem, 75. The upper bound is 75. The mean is still 72, and the standard deviation is 2. So let me zoom in so you can clearly see what's going on. Here's the lower bound of negative infinity. Here's the upper bound of 75. Here is the mean, and here's the standard deviation. So I push enter, and I get 0.933193. So this one should be 0.933193 or 93.319%. That's what your answer is for part A. Oh, no it's not. I typed in the wrong upper bound. Oh my gosh. Cancel that. I don't know what I was thinking, guys. Why'd you let me make that mistake? Okay, so let me go back here. Can you guys find my mistake? Anybody? My upper bound is supposed to be this number, not 75. I apologize about that. So, your answer is 0.066807 or 6.6807%. That's your percent. Part B. Approximately what percent of WNBA players are taller than 76 inches? So let me draw my reference diagram. The mean is at 72. 76 is somewhere here on the right, and we're looking for taller than 76. So I'm looking for the area of the graph shaded to the right. My lower bound is 76. My upper bound, this goes all the way to positive infinity. Okay? Or in calculator terms, 9E999. So let me try not to make the same mistake again. I'm pushing the arrow button twice. My lower bound goes first. It's 67. comma, upper bound, oh my gosh, I almost made the mistake. Wrong problem, Megan. Part B, my lower bound is 76. My upper bound is positive infinity, so 9E999. There you go. 76 is the lower bound. Upper bound is 9E999. 72, we're still working with the same mean and the same standard deviation. So your answer is right there. 0.022750, or if we move that 2 places, 2.275%. So this one is 2.275%. Okay. I'm not going to worry about part D. Just for extra practice, I'll do this one for you, just in case we need extra practice, anybody watching the video. Okay, so now we're moving from the WNBA to the NBA. The NBA players have a mean height of 79 inches and a standard deviation of 3 inches. Oh, that just says the same thing again. I don't know why I put that in there. Okay. So approximately what percent of NBA players are taller than 80 inches? Let me draw my curve. My mean is at 79. If I move 1 inch to the right, that's going to be 80, and we're looking for taller than 80. So we're looking at this piece right here. Your lower bound is going to be 80. Your upper bound, this is one of those cases where it goes to positive infinity, or 9E999. Okay? And I'm just going to write this here. Your mean is 79. Your standard deviation is 3. So I don't make a mistake. Let's go ahead and plug that in. Lower bound goes first, and it is 80, comma, upper bound is positive infinity, or 9E999, comma, your mean is 79, and your standard deviation is 3. So let's zoom in. For the answer, I'm just going to push enter, and I get 0.36944, or 36.944%. 36.944%. Okay. I think these are a little bit easier whenever we don't have an infinity involved. So part F, approximately what percent of NBA players are between 76 and 84 inches tall? Here's my curve. The mean is 79. So we're looking at around 76 to 84. I imagine that number is going to be pretty high. There's a lot of data in this piece right here. So your lower bound is 76. Your upper bound is 84. So those are the only two numbers I have to change. 76, comma, 84. Yep, I'm right. This number is much bigger than the last one. We get 0.793554, or 79.355%. 79.355%. I'll go ahead and skip that one for you. See if you can practice it, and the answer is 9.112%. If you're interested. Is that right? Well, let me check. Yeah, I think that's right. Yep, that's right. 9.112. I want to talk about part H. The tallest WNBA player, back to the women's league, is 80 inches. The tallest NBA player is 87 inches. Which of these heights is more unusual? Okay. So, what you can do is, one option is we find their z-score and find which one is farther away from the mean. The other option is we find what percentile they are in. So percentile means basically you find out what percent of people are they taller than. Okay? So if this is where 80 inches is, you're going to find how many the area under the curve to the left. Okay? Let's just go with the z-score option, because why not? WNBA, I'm going to have to refresh my memory. That has a mean of 72 and a standard deviation of 2, and our data value is 80. So the z-score is 80 minus 72 divided by 2, or 4. For the NBA, the mean is 79, the standard deviation is 3, and our data value is 87. So the z-score is 87 minus 79 divided by 3. So 8 divided by 3, or 2.667. Oh, looks like this lady is farther away from the mean. So she is somewhere way over here, and this guy is only like right here. So here's the WNBA, and here's the NBA. So it's way more unusual to be 80 inches in the WNBA than it is to be 87 inches in the NBA. Right? That is it. Have a good night, guys. Bye.